So today we will be looking at the summary of errors. We would like to summarize errors. All the things we have been doing so far is concerning Maths 209, and today we'll talk about the summary of errors. So, like I said earlier before, I said that errors arises due to what? Due to mistakes in mathematics or mistakes in calculation. Error arises due to mistakes in mathematics or mistakes in calculation. I said that on the number line, we have 1, we have 2, we have 3. These are exact numbers. Exact numbers, because any number that you can trace on the number line, they are known as exact numbers. But for example, if I now have something like the square root of 2, like this, if you were to give me the square root of 2, you give me a decimal place. Or let's say, for example, if you were to give me pi, which is 22/7, you say it's 3.14 whatever, right? So these numbers, as they are decimal, cannot easily be located on number line. They cannot easily be located on number line. That is where approximation comes in. The word approximation. That is where the word approximation comes in. Is that clear? And so we're able to find out that error. In a calculation is the exact value. Do you see that? The exact value minusing the approximate. Minus the approximate value. And so we cannot deal with calculations if we cannot find out or know the difference between a significant figure and decimal place. These are two major concepts we need to look at very quickly. So I said that a significant figure, let's write that out quickly. I said a significant figure, let's write that. Significant figure. A significant figure, as it were, is a non-zero digit. Did you see that? A significant figure is a non-zero digit in its decimal representation. Right? So let's say, for example, 1 is a significant figure. 2 is a significant figure. 3 significant figure. 4 is a significant figure, and so on and so forth. But 0 in itself is not a significant figure. The only time you can have 0 as a significant figure is when you use it in two different use cases. And so we are going to be looking at those quick use cases right now. Number 1, what are the laws that guide a significant figure or that qualifies significant figure? Laws. So we say laws of significant figure. Did you see that? What are the laws of significant figure? Number 1, we said whenever, did you see that? Whenever a 0 lies between, did you see that? Whenever a 0 lies between two non-zero digits, whenever a 0 lies between two non-zero digits, he said we should regard it as a significant figure. What does it mean? It means that whenever I have, for example, 505, what it's trying to tell me now is that I should regard this as a what? As a significant figure, because this 0 is lying between two significant digits, right? I said first of all that significant figures are non-zero digits, right? So 5 is a non-zero. The other 5 here is a non-zero. As long as 0 is in the middle, we can regard it as a significant digit. Is that clear? I said number 2, this is number 1 law. Number 2, I said whenever 0, did you see that? whenever 0 lies on the right, whenever 0 lies on the right hand of a decimal point, lies on the right hand of a decimal point, and at the same time, to the right hand of a non-zero, did you see that? Digits. At the same time, the right hand to a non-zero digit, then you should regard it as also a what? A significant figure, right? So what we are saying now is, for example, is when we have 7.00. Now, this, as it were, this part of the equation is the left hand side, right? Your left hand, your right hand. These sides are what? Your right hand side. So we are saying that whenever 0 at its way, which are these zeros, are lying on the right hand, which is, this is the right hand of a decimal point. These are decimal points. And at the same time, on the right hand of a non-zero, look at, this is a non-zero, 7 is a non-zero. So we regard them as what? Significant figures. So if I were asked, or you were asked, what or how many significant digits are here, you will say 3 significant figures are here, which are 7, your 0, and your 0. Are we there? So as we continue, we now progress and said the third law states that whenever we have standard form, in the sense that m, when multiplied by 10 raised to power n, we said all the entities, did you see that, in m is regarded as what? Significant figures. Is regarded as significant figures. With these few points, let us look at some basic examples of what I just said. Let's look at some basic examples of what I just said. Now, we have numbers, we have significant figure, let me spell that well, significant figures, and we have number of significant figures. So let's quickly do that quickly. Let's assume that we have 37.89. So the question I'm going to be asking you is, how many significant figures are present here? Or what are the significant figures present in this expression? 37.89. We have 3. 3 is a significant figure because it's a non-zero. 7 is a significant figure because it is a non-zero. 8 is a significant figure because it is also a non-zero. And what? 9 is a significant figure because it's a non-zero. So the total number of significant figures we have here is 4. The next one is when I say 5090. How many significant figures are here? 5, as it were, is a non-zero. Now, are we going to regard this 0 here? Yes. Why are we regarding it? I said in law number 1, I said when 0 lies in between a 2 non-zeros. These are 5. 5 is a non-zero. 9 is a non-zero. This 5 here is a non-zero. 9 is a non-zero. So whenever 0 lies in between 2 non-zeros, he said we should regard it as a significant figure. But we will not regard this. Why? Because it's not obeying the law. So the significant figures we have here are 0 and 9. So that's 3 significant figures. Again, let's look at 0.00082. Did you see that? 0.00082. So you said, if you want to know how to do this, you can simply just turn this to standard form. then you'll be able to refer to law number 3. Law number 3, which states that whenever we have m times n to the power of n, all the entities in m is a significant figure. So let's look at that together. Let's look at that quickly together. So we have, let's move this decimal place, 1, 2, 3, 4. This is 8.2 times 10 raised to the power minus 4, right? Now, if that's 8.2 times 10 raised to the power minus 4, then we ask ourselves, these are the elements, or these are the entities in n. Let's correlate it to the formula. The formula says m times 10 raised to the power of n. So this person is correlated to these people here, right? 8 and 2. So all the elements here, which are 8, and 2, are significant digits. And so we find out that the number of significant digits here is what? Is 2. Is that clear? So the same thing goes for other examples that you might come across when it comes to what? Significant figure. Let's look at this together. We have 3.509 times 10 to the power of 4. All the elements in m, this part, all the elements in m are significant. So what we can say here is that significant figure here is 3, 5, 0, and 9. So what we have is 1, 2, 3, 4. 4 significant digits, right? So this has made us have a solid background of what significant figures look like and how we solve the problems in significant figures. The next thing we are going to do is the rounding off of numbers. So let's look at that concept together, because all these things are the foundation of error. So let's look at it together. Rounding off of numbers. Rounding off of numbers. Rounding off of numbers. So we said rounding off. Rounding off. We said the process. We said the process of cutting. Did you see that? Cutting large numbers, or cutting the numbers short by approximation is rounding off. It's called rounding off of numbers. And so there is a basic rule that is applied here. There is a basic rule that is applied here. We said whenever you are dealing with elements that are in the range of 0 to 4, we said you should round it off to 0. Whenever you are dealing from 5 to 9, we said you should round it up to 1. Rounding off of numbers. So let's look at that quickly together. For example, let's assume that this is a number here. Now we have 0.52231. Now, how do we round this up to 3 significant figure? 3 significant figure. What transformation do we need to use? So we find out that to change this or to round it up to 3 significant figure. Now, you can look at here, we say 1, 2, 3, right? To 3 significant figure. But we discover that this 3 is not, you can see 0 to 4 is within the range of 0 to 4, 0 to 4. So it is regarded as 0, round it up to 0. So in 3 significant figure, what you now have is 0. Did you see that? 522. 3 significant figure. If you are still doubting, I said anytime you have a decimal place like this, I said convert this now to standard form. If you convert it to standard, you have 5.22341 times 10 raised to power what? Times 10 raised to power minus 1. Is that not? Now, if you have been able to do it like this, then this is a non-zero, a significant figure, a non-zero, a non-zero, a non-zero, a non-zero, a non-zero. So it's all these elements here in M. All these elements here are significant figure, but we are doing 3 significant figures, so we need to approximate. And so when you do that, what you are going to have is what? You're going to have 5.22, because 3 is not up to See 3 falls between the category of 0 to 4, so we approximate it to 0. So we have 5.22 times 10 raised to power minus 1, which is still the same thing as this. Is that clear? So the next number we'll be looking at, is 93.2155. 93.2155. What is our solution to that? To three significant figure. You can tell me. Our answer will be what? 93.2. Why? Because this particular person falls between the category of 0 to 4, and so when we round off any numbers that come between this category, it's regarded as 0, and so you're going to be having 93.2. Is that clear? So this illustration has given us a background check on what we should be expecting when it comes to rounding off of numbers. So from here, we'll be able to illustrate what error is. We'll be able to illustrate what errors are. All right. Errors. So we said errors, by definition, or error, is the true value. Is the true value, did you see that? Minus the approximate. Error is the true value minus the approximate. And we have types of error. The types of error that we have: number one, we have an inherent error. Number two, we have analytical error. Number three, we have what we call the round off errors, right? So and so forth, right? Now we will be looking at questions. On how to apply these functions. Mind you, there is something called absolute error. So we have absolute error. Absolute error is us using the sign true value minus approximate value. Did you see that? True value minus approximate value. And so absolute error does not give you anything negative. The word absolute, for example, if I ask you what's the absolute value of minus 2, your answer is 2. What's the absolute value of 2? Your answer is 2. Why? Because absolute, the word absolute tells us about the positivity. Just take the non-negative function of that number. So if I say, what is the absolute value of minus 2? Your answer will be 2. What is the absolute value of 2? Your answer will still be 2. If I say, what is the absolute value of minus 5, for example, absolute value of minus 5, your answer will still be 5. So we are simply telling you that absolute error is what? The non-negative, the non-negative part of errors. Okay, so we now said that there's something called relative error. And what is relative error? Relative error is absolute error. Did you see that? Absolute error when you divide it by exact values. Did you see that? When you divide it by exact value, which simply means that by definition, we're simply saying true value minus approximate. True value minus approximate value. Approximate value should divide exact value. That is the only way you can record relative error. Now, the word absolute, like I earlier said, is the non-negative part of a function, which you can also write with the symbol triangle. So if I say, let's clean the board quickly. So if I say the triangle of x, what I simply mean there is the absolute value in x, which means the exact value of x minus the approximate of x. If I say the y, that's absolute value in y, the exact value of y minus the approximate of y. If I say the z, change in z, it means the exact value of z minus the approximate of z. So that is how the functionality of absolute error occurs. Let us look at some samples. From here, we'll be able to look at some very definite samples of what we are saying. Okay. They said if the x is equals to 0.005 and the y is equal to 0.001, be the absolute, did you see that? Be the absolute error in x equals 2.11 and y equals 4.15. Did you see that? It says find the relative. It said find the what? The relative error. And so how do we find the relative error of this function? We said that's what? Okay, find the relative error in computing. Let's complete the question. Find the relative error in computing x plus y. So emphasis on computing, the word compute, x plus. So whatever this thing says is what we are going to do. The plus sign here. Let's notice the plus sign. So whatever it says is what we are going to do. So what is the formula? Remember, we are finding relative error. So what is the formula for relative error? We said the relative error is absolute error over exact value or true value, whatever the case you want to call it. And so we have two basic absolute error here, which is the change in x and the change in y. And so because we are computing plus, we're going to add the absolute errors. So change in x should be added to change in y, and then you divide. So what is the exact value? The exact value is x plus y, right? And so we find out that the change in x is 0.005, and we add it to the change in y, then 0.001, and then we were able to divide. Did you see that? We were able to divide it by 2.11 plus. So the value of x itself is 2.11, and the value of y is 4.15 plus 4.15. And so this gives us a round figure of 0.006 divided by 6.26. And so our final answer to this function is 0.000958. Did you see that? So that is the relative error of that function. So let's look at some other basic and notable examples that we can derive from this. Look at another notable example that we can derive from this. Errors or mathematical functions are very interesting concepts. Very interesting concepts that I would love for you to understand. I would love for you to be able to solve them without any hitch. Let's look at some basic questions. The first, it said, approximate, did you see that? It said, approximate the following to two decimal places. Number one, 33.54637. We want to approximate it to two decimal places. Now, no longer significant figure, but what? Decimal places. So, to two decimal places, the approximate of this function to two decimal places is 33.55. I hope you know. This is the approximate. This is the approximate. Now the question says, after you have approximated, make sure to find the error involved. Make sure to find, number one, you want to find the error involved. Number two, you want to find the absolute error. Number three, you want to find the relative error. And number four, you want to find the what? The percentage error. So let's do that quickly. So how do we find the error involved? Okay. We now remember, we're able to remember that the error involved is equal to the exact value or true value minus approximate. Did you see that? Exact value minus true value minus the approximate. So the exact value is the question itself, that's 3.54637, and then we are taking away or minusing 33.55, which is the approximate. And so from there, you will find out that the error involved is negative 0.003631. Is that correct? You can clarify that in your calculator. And so we want to find the absolute error. I've told you before that the absolute error is just you taking into account exact value minus approximate. Did you see that? Exact value minus approximate, which simply means that we are taking into account this figure, negative 0.003631. And so when you deduct the minus from it, absolute error takes care of that minus, removes the minus. Did you see that? Removes the, so the absolute error in this function is 0.006331. Is that clear? And so now that we've been able to find out what the absolute error of the function is, it is now left for us to find out what the relative error is. What would be the relative error? Then we'll be able to say that the relative error will now be absolute error should divide the exact, did you see that? The exact value. And so if you put this into consideration, you'll be able to find out that this is 0.003631. Did you see that? Should divide, and what is the exact value? This value, 33.54637. And so from there, you find out that you have 0.000108 whatever, right? This is the relative error. So class, if I ask you what will be the percentage error, what will be your percentage error? We know from our definition that percentage error is the relative error times 100. The relative error times 100 over 1. So the relative error, as it's where here, 0.000108 times 100. And so we are going to find out whatever it is. So whenever you use this to cancel two of these, so this will be 0.0108. You can put percent there, right? So that is that on the basics of error. So we'll find out that the basics of mathematics is the fact that we can make mistakes, the fact that we can arrange numbers, the fact that we can subtract, add, multiply, or divide numbers. I hope this is clear now. All right, so see you in our next video.